Section 20. Okay, we talked a lot about numbers. Now let's talk about categories. So suppose you've got a categorical variable. It could be something as simple as people who are left-handed or right-handed. And you want to test a theory about the population in question. Maybe you want to test the theory that 10% of people in the United States are left-handed, for instance, and 90% are right-handed. Or it could be many categories, and we'll do some more interesting examples later. So you have a particular understanding of how the categories play out, and you want to test that to see whether the sample that you have is consistent with that theory. So you've got the theory that 10% of people in the United States are left-handed and 90% are right-handed. And you've got a sample, let's say, of 100 people, and 8 of them are left-handed and the rest are right-handed. Is that consistent with your understanding that 10% of people are left-handed? Well, let's think about it. If you pick 10 people and 2 of them were left-handed, that is 20% of the sample, that wouldn't necessarily be evidence against your theory that 10% of people in general are left-handed. It's just the luck of the draw. You got an extra left-handed person out of 10. On the other hand, if you picked 1,000 people and 80% of them, 800 of them, were left-handed, then that would make your theory that 10% of all people are left-handed a little hard to believe, right? So this is the idea. Is your sample, are the proportions in your sample consistent with your theory, or do they count as evidence against it? This is how the goodness of fit hypothesis test works. The hypotheses here are H0, the categories are distributed as expected, and HA, the categories are not distributed as expected. They're distributed in some other way. Notice here we're getting away from the equality versus inequality formulation, but we still have the idea that the null hypothesis is singular, and the alternative hypothesis is very plural. H0, a particular understanding of how the facts play out in the real world. For instance, 10% of people are left-handed, 90% are right-handed. HA, every other possible understanding. It is not the case that 10% of people are left-handed and 90% of people are right-handed. The proportions are something else, something else. As always, we assume H0 in order to run the numbers, so you have to assume particular facts in order to do that. H0 is the kind of thing you can assume to run the numbers. 10% of people are left-handed, the rest are right-handed. HA is not the kind of thing you can assume to run the numbers. So it makes sense. The test statistic here is a different kind of test statistic. We've talked about z-test statistics, we talked about t-test statistics, but here we have a different kind of test statistic which is called the chi-square statistic. And the chart for the chi-square looks very, very different from the z-chart and the t-chart. It's not symmetrical. This density curve goes off in one direction. It starts at 0, and then it trails off forever to the right. This makes sense if you think about it. There's nothing bidirectional about this kind of statistic. Under, over. No, it doesn't work that way. We have only being in perfect accordance with, we have only the sample being in perfect accordance with your theory, and the sample being increasingly out of alignment with your theory. So it's a very one-directional type of statistic. But as before, it will be the area of the tail being small, the tail being off to the right, which makes your theory of H0 hard to believe. So the basic logic of hypothesis tests always plays out the same way. Assuming H0, what's the probability of a sample as weird as ours? P-value. If it's very low, for instance under 5%, then you reject that theory. Otherwise, the theory is still plausible. You find evidence of the alternative, otherwise you don't. So all that really remains is how to compute the test statistic, how to use the chart, and the rest is pretty much exactly the same as before. So the way this works is that you have, for the sample that you are actually looking at, say 100 people who may or may not be left-handed, you have the observed counts. You have the number out of 100 who are left-handed, the number out of 100 who are right-handed. The sample, what you've actually observed. And then you have what you would expect to find if your theory were true. For instance, if you have a sample of size 100, and it is true that 10% of people are left-handed, then left would be 10 people and right would be 90 people. If it were a sample of size 200, and your theory was that 10% of people are left-handed and 90% were right-handed, then in a sample of 200 you'd expect to find, under ideal conditions, if you landed dead center, 20 people, that is 10% of 200, left-handed, and the rest, 180, right-handed. So that's the idea. And I should note that if you've got a sample of a weird size, 17 or whatever, and these are not going to work out to be whole numbers, then for mathematical purposes, don't round them. Keep them as accurate as they have to be. So it's okay if you've got decimals involved here, even if it doesn't make logical sense that you could have, say, 5.7 left-handed people. Nevertheless, keep those numbers, keep the accuracy all the way through. As always, round as little as possible until you're done. So the way that the chi-square statistic is computed is that for each category, whether it's as simple as left-handed, right-handed, or whether it's 20 different majors in a university, but for each category, we figure out what you're actually getting, the observed count, minus what you would expect for a sample of that size, square it, and then divide it by that expected count again. I'll get it yet. There it is. And then add them up. Notice, by the way, that these are all positive numbers. I mean, numbers of counts in a category are obviously positive numbers. And if you, well, you're squaring this, so the top is positive anyway. So this is the sum of a bunch of positive numbers, which is itself positive. The chi-square statistic is always at least 0. And then it trails off to the right with bigger examples of a chi-square on our horizontal scale here. The degrees of freedom is 1 less than the number of the categories. Again, like the t-distribution, there are many chi-square distributions. Here we see a few of them. We've got, in black, the t-distribution, the chi-square distribution with 1 degree of freedom. In blue, the chi-square distribution with 2 degrees of freedom, and so on and so on and so on. You can see how the shape gradually contorts there. The degrees of freedom is 1 less than the number of categories you have. This is common sense. If I have a sample of size 200 and I tell you that 20 people were left-handed, then obviously the rest of them were right-handed. If you know one, you know the other. If you've got 10 categories and I give you the counts in any 9 of them, then you know the count in the last one. It's the rest. So logically, the degrees of freedom, how many things you can freely choose, and then the remaining one will be determined by it, is 1 less than the number of categories. If anything, it makes more sense than when we were talking about it in the t-distribution. So that is the idea of the theory of the chi-square distribution. For a given sample size, how many counts would you expect at each category if your theory were true? And again, don't round those. If they're not whole numbers, it doesn't matter. For mathematical purposes, keep the accuracy. Then we can compare them to the actual counts. So the logic of the chi-square test is, assuming that the categories for the population are distributed as you believe they are, for the sake of argument, it is true that 10% of people in the United States are left-handed and 90% are right-handed. If that is true, assuming that is true, How weird is it to get a sample as out of alignment with those counts as we expected? If you run a sample and about 10% of people are left-handed and about 90% of people are right-handed, then your theory is looking pretty plausible. But if you run a sample and you get something very different from 10% left-handed and 90% right-handed, that is very different from what you would expect if your theory were true, well, the more out of alignment your sample is with what you believe the facts to be, the more implausible, the more suspicious your theory of the facts becomes. So that's the logic of the chi-square test, and all that remains is to do some examples. Example 1, we roll a die 600 times and we observe the counts below, which I'll give you. Does this suggest that the die is fair? Now, in the past, we've cheated on this a bit. We said that a fair die would have mean 3.5, but it's possible, if you think about how we played this out in section 5, as long as those bars are symmetrical, 1, 2, 3, 4, 5, 6, the mean is going to be 3.5, even if all the bars aren't necessarily the same height. You know, bar, 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 bar. So there are a lot of different combinations of bars you could have on those 6 faces of the die, which give you a mean of 3.5. But what we really mean by the die being fair is that every one of those numbers comes up the same proportion of time in the long run. For a cube, 1/6 each. Also notice that this has got nothing to do with numbers. These are categories. You can take a cube and you can put 1, 2, 3, 4, 5, 6 on its faces, or you can put different colors on its faces, or you could put different pictures on its faces. In no sense are we using the numbers. We only want to know that a fair die would be one where each face would come up 1/6 of the time in the long run. Any way you want to distinguish them. The face with the 1 on it, the 2, the 3, the 4, the 5, the 6, the red face, the yellow face, the green face, etc., or 6 different pictures, they are categories. We are not using the fact that typically they have numbers on them. We are not using them as numbers. They're just little drawings of numerals on each side. They might as well be colors or anything else. A fair die is one where each category, each of the 6 sides of the die would come up 1/6 of the time in the long run. So for 600 rolls, then under ideal conditions, you'd expect about 100 each. But we'll run the numbers. What we actually get is right here. The 1 comes up 90 times, the 2 comes up 110 times, the 3 comes up 95 times, the 4 comes up 120 times, the 5 comes up 90 times, the 6 comes up 95 times, for a total of 600 rolls. Now again, notice that this is nicely divisible by 6, but that's neither here nor there. If the expected counts don't come out to be whole numbers, just leave them, don't round them. So at a glance, it looks like you've got about 100 of each, but of course, that depends on the context. You can't really tell at a glance. A few over under the ideal is not that noteworthy for small samples, but very significant for large samples. So you can't necessarily tell at a glance whether this suggests that the die is fair or not. All we know for sure is that if we roll a die 600 times, it's highly unlikely that you're going to get exactly 100 of each. I mean, for instance, if you roll a die 6 million times, it is highly, highly unlikely you're going to get 1, 0, 0, 0. Try again. If you roll the die 1 million times, it's highly unlikely that you're going to get 1, 0, 0, 0, 0, 0, 0 of each. It's just too on the nose, right? It is the ideal. It is what you would expect under ideal conditions, but you wouldn't, for a large sample anyway, you were probably never going to land exact. So, of course, there is going to be random variation in the sample. That's always the name of the game. But if these counts are highly out of alignment with what you would expect a fair die to do, then you'll reject the theory that it's a fair die. If the counts are not all that out of alignment with what you would expect a fair die to do, then what I say, not out of alignment, then it's still plausible that it's a fair die. So we'll organize our facts here. Well, basically that's what I'm saying up here. If the counts are very out of alignment with what you'd expect a fair die to do, we'll reject the theory that it's a fair die. That is to say, if the die being fair would make a sample this out of alignment with the ideal highly unlikely, then it's probably not a fair die. And that's our p-value, the probability of getting a sample as out of alignment with 1/6 each as we did, at least as out of alignment with 1/6 each. On the other hand, if they're not all that out of alignment with what you'd expect, then it's still plausible the die is fair. Don't reject H0. So in the goodness of fit hypothesis test, H0 is always that the categories are distributed as expected. In this case, fair die 1/6 each. Now again, it doesn't necessarily have to be the same proportion each. You could do 10% of people are left-handed, 90% of people are right-handed. We'll do some other examples later, and there's a nice selection in the practice problems. But let's start with the simple example of each category coming up the same amount of time in the long run. Fair die, 1/6 each. And then HA, the categories are not distributed as expected. The die is unfair in some way. Something other than 1/6 each for each of the faces is the truth in the long run. And again, in red, basically what I've just said here, you could have three categories. You could have 10% of people are left-handed, 85% of people are right-handed, 5% are ambidextrous. So you could have three categories, and you could work out the numbers. Under ideal conditions, if you had a sample of size 100, then you'd expect 10 of those, and 85 of those, and 5 of those, etc. But for now, let's stick with the equally likely categories, 1/6 each, fair die. So we've rolled the die 600 times, and these are the counts we've actually gotten. If it is true that it's a fair die, that is to say, if it is true that each category comes up 1/6 of the time in the long run, then you would expect 1/6 of the 600 to be ones, 100, yeah, correct. 1/6 of the 100 to be twos, and so on, and so on, and so on, and so on. I'm trying to say this in a general type of way, but of course the simple way to say it for a fair die is that if you roll it 600 times, then you'd expect 100 of each. So we have our observed and expected counts, this is not going to let me highlight, so I'll just circle around here. Observed and expected counts. If what you're actually seeing is very out of alignment with what you would expect a fair die ideally to do, then we'll reject the theory that it's a fair die. If the observed and expected counts are in context not that different from one another, then it's still plausible that the die is fair. So we'll run the numbers using the formula that we've talked about. Now this can be a little bit more tedious than some of the other hypothesis tests, but what the heck, it's all online now. So first we'll compute the observed minus expected for each one. Now be very literal about this. I mean, when we square it, the sign is not going to matter ultimately, but it's nice to get it right. 90 minus 100 is negative 10. 110 minus 100 is 10. 95 minus 100 is negative 5. 120 minus 100 is 20, and so on and so on and so on. So these represent how far we deviate from the ideal for each category. Square them, which of course loses the sign. 100, 100, 25, 400, 100, 25. Now divide by expected. 100 minus 100 is 1. Ditto. 25 minus 100 is 0.25. 400 minus 100 is 4. 100 minus 100 is 1. 25 divided by 100. Have I been saying minus? Let's try again. 100 divided by 100 is 1. 100 divided by 100 is 1. 25 divided by 100 is 0.25. 400 divided by 100 is 4. 100 divided by 100 is 1. 25 divided by 100 is 0.25. And then add them up. 1 plus 1 plus a quarter plus 4 plus 1 plus a quarter is 7.5. Notice that we can see pretty clearly at this point that it's the 4 that seems to be more out of alignment than the others, which may or may not signify anything, but anyway, it adds up to 7.5. So there is my chi-square statistic. The chi-square test statistic is 7.5. It is the bigness. They're positive. They're all positive. It is the far awayness from 0. It is the extent to which this is bigger than 0 that makes things suspicious. In other words, the tail is to the right. 7.5 is what, here-ish? And then we're talking about this tail over here. If it's small, it counts against H0. If it's not all that small, it doesn't count against H0. That part never changes. The degrees of freedom is 1 less than the number of categories, 5. So, well, obviously, if you know how many 1s and 2s and 3s and 4s and 5s you got, then the rest of them are 6s. So you can freely choose 5 of these for a given sample size. These software links are kind of dead on the website, so I have put up a new one on Blackboard, and I'll show you that in a minute. But first, let's talk about the chart method. So you find the p-value corresponding to 7.5 for the chi-square distribution with 5 degrees of freedom. So first of all, we can do this using charts. We'll go to the chi-square chart on my website, blow it up a little bit. So on the degrees of freedom 5 line, we're tracking down 7.5, I think it was. Yes. Notice again, although everything is positive, it is still true that a large test statistic cuts off a small tail. This should be comparatively obvious, right? The test statistic starts at 0, and then as you go off to the right, it becomes a bigger and bigger number. And consequently, as it becomes a bigger and bigger number, it cuts off a smaller tail, a smaller area to the right. If you're over here at 1, then you cut off a pretty big tail to the right. If you're over here at 7, you cut off a pretty small tail to the right. The only difference is we're only going in one direction this time. So we're tracking down 7.5 on the degrees of freedom 5 line. And there it is, between the 6.6 something and the 8.6 something. So the area to the right, the corresponding p-value, is between 1.25 and 0.25. There are hypothesis tests that use the area to the left, but we're not going to talk about those in this course. We're always going to be finding our p-value on the chi-square chart as the area to the right. So that should be all summarized here with the chart method. There it is. So because our 7.5 is between those two entries, our corresponding tail is between 12.5% and 25%. Which is enough to tell you what you need to know, right? Assuming that it is a fair die, you would get counts as out of alignment on a sample of 600, as we did. Well, between 12.5% and 25% of the time. So it's just not that strange. As we might have suspected in the first place, this is just not all that out of alignment with 100 each. So again, the p-value represents the probability, assuming that your theory is true, assuming the die is fair, what is the probability of rolling it 600 times and getting counts as out of alignment, at least as out of alignment with 100 each as we did? Well, it would occur between 12.5% and 25% of the time that you rolled it. 600 times. So, well, at the 5% level, for instance, or even the 10% level or the 1% level, if it's more than 12.5, it's just not suspiciously small. In particular, at the 15% level, sure, maybe, but here we're doing the 5% level, and our p-value is definitely not less than 0.5. So we will not reject H0 and find no evidence of HA. We will not reject the theory that it is a fair die. We will find no evidence that it is an unfair die. Now, if you do want to use software to compute these, there is a chi-square calculator that will actually work for the moment on my Blackboard. So go here to the chi-square calculator link. It should be described. This might be a little bit confusing. You can click on the header at the top here, and that'll take you to the actual calculator. That's a little unfortunate, but this is supposed to be a hyperlink here. This just details how the calculator works. So click on it, and what are we talking about? Degrees of freedom, 5. Obviously, I've done this before. And we'll type in 7.5 into our calculator. This may or may not be the example that's actually illustrated here. It is. So we'll type in 5, 7.5, and then hit compute. Now, again, we're interested in the greater than. So this is giving me, we're not interested in the area to the left. We're interested always, for our purposes, in the area to the right, the greater than. So 0.19. This particular calculator doesn't give me the 3 decimal places that the one that I used here did, but yeah, it's about 186. This particular chi-square calculator is calling it 0.19, which is probably good enough for our purposes. So if I track down any chi-square calculators that are a little bit more accurate, I can put those up as alternate resources, just in case 2 decimal places isn't enough. But there is always the chart method. So we've got the 0.186, or in our case, the 0.19 from our calculator. Again, this is all spelled out here. You don't want the area to the left, you want the area to the right. So yeah, if you can explicitly compute that 0.19 or 0.186, then obviously it's not less than 0.5, so you're not going to reject H0, and you're going to find no evidence of HA. Conclusion would be the same at the 1 and 10% levels. I mean, it's more than 12.5%. It is, in fact, 19%. It's not less than 1% or 10%. A sample of 600 rolls coming up this out of alignment with 100 each is just not that suspicious, so it's still plausible that it's a fair die. Example 2, all I'm going to do is change the numbers. I'm going to take a different sample of 600 die rolls, but the superstructure of the problem plays out exactly the same way. In this case, of our 600 rolls, 85 were 1s, 112 were 2s, 95 were 3s, 125 were 4s, 88 were 5s, and the rest, 95, were 6s. As always, for 600 rolls, you'd expect 100 of each, if it were a fair die. Same H0, same HA. So now we'll run the counts. Observed minus expected, negative 15, 12, negative 5, 25, negative 12, 5. You can already see the numbers are a little bit bigger than they were, in size anyway, than the previous example. Although there is nothing as, well, the 25 is a little bigger than the 20, yes. Square them, and now you can definitely see this amplified. The numbers are coming out a lot bigger. Squaring, of course, will amplify sizes. It'll make big bigger. So square the negative 15, well, ultimately the negative will be irrelevant, of course. So we get 225, 144, 25, 625, 144, 25. Divide them by what you would expect, 100. That's relatively easy. Just move the decimal place, right? 225 divided by 100 is 2.25. 144 divided by 100 is 1.44. and so on and so on and so on and so on. Now when you add all these up, you get 11.88, which of course, considering we're using the same exact chi-square curve as before, is a lot further along. So now we've got our chi-squared of 1188, still 5 degrees of freedom, with our chart method. Which one is that? This one. What did I say, 1188? So on the 5 degrees of, on the 5 degrees of freedom line, there we go. I'm looking for mine like a sieve, 1188, which is there. So the corresponding p-value is between 5%, between 2.5% and 5%. Well, it is less than 5%, it is less than 10%, it's not less than 1%, but more on that in a minute. In particular, it's between 0.25 and 0.5, at least that's what's supposed to be. Yeah, here it is. So on the 5 row, it's between these two entries, so consequently the tail, which is to the right in these tests, is between 2.5% and 5%. That's enough for the three basic levels, right? It's less than 5%, it's less than 10% as a consequence, and if it's bigger than this, then it's not less, if it's bigger than this, then it's not less than 1%. So at the 1% level, well, if it's more than 225, it's not less than 1. So at the 1% level, we will not reject H0 and find no evidence of HA. If your sample has to be among the 1% weirdest you could have gotten on the theory that it's a fair die, we're not there yet, and it's still plausible that it's a fair die. We have no evidence that it's unfair. On the other hand, if your sample has to be among the 5% most out of alignment with what you would expect a fair die to do, then we are there. Our p-value is less than 0.5 explicitly, so we will reject H0 and we will find evidence of HA. Just a slightly different standard. How weird, 1%, 5%, how weird does your sample have to be before it counts against the theory? Is it among the 1% weirdest? No, the theory is still plausible. Is it among the 5% weirdest? Yes, the theory is no longer plausible. We will reject H0, we'll reject the theory that the die is fair, and we will find evidence that the die is unfair. So that's, alternately, we can compute the p-value, and I'm sure this is not going to give us 4 decimal places, but let's see what we can do with it. We'll go to the chi-square calculator, 1188, 5 degrees of freedom. So 1188, 5 degrees of freedom. I may have to physically blank these out. I don't know how picky this is going to be. Let's find out. No, it's not going to let me do that. But let's at least blank this one out. And then run the numbers. 1188, 5 degrees of freedom, hit calculate. There you go, I had to hit it a couple times. And yeah, that's not ideal. Oh, sorry, I've got this backwards. 5 degrees of freedom, 1188 for the chi-square value. I'm going to blank this one out just so it doesn't confuse it. I see, if I click anywhere else, over here for instance, then that'll blank it out. And now if I hit calculator, 0.4. Yeah, good enough, not ideal. If it were 0.5, it would not be great, but certainly good enough in this case that 0.4 on my previous, 0.365, it rounds the same. Certainly in this case, 0.4 is enough to answer the question. 0.4 is less than 0.5, it's a little close, and it's not less than 0.1. So you can always use the charts. The charts will give you enough information. Bear in mind that it's not a question of rounding with the charts. It's highly unlikely that you're going to hit these 3-digit things, 3 places after the decimal things dead on. So you don't really have to worry about it too much with the chart method. I will see if I can track down a chi-square calculator that is not too cumbersome to use and which will give more than 2 places. But generally speaking, StatTrak is a pretty good site for these calculators. Unfortunately, in this particular case, it doesn't give us a great degree of accuracy, but there's lots of other websites out there. So there's a couple of examples of a chi-square distribution. I want to put up a further one on my website just to clear up any misconceptions. I would like to put up something more aligned to the, more akin to the one that I talk about here in the red, where the categories are not all a sixth each, etc., where you've got a little bit more freehand on the percents, just to clear up any misconceptions, because these particular examples, we have categories that are all equally likely, which does simplify this a bit, but that certainly doesn't necessarily have to be the case. And for the practice problems on my website, there should be a nice selection of those. 5%, 85%, this is more like the left-handed, right-handed thing. This is, an 8-sided unfair die, so an eighth each. 40% with brown here, 35% with dark brown here, and so forth and so on. So this gives you a better idea of what these things look like. As always, of course, these curly quotes are a bit of a problem, but hopefully that shouldn't be too big of a deal. That's easily fixed, but I might have to put the menu bar back. View, text encoding, Western. Okay, that fixes the quotes, but in any case, you can figure it out even with the curly quotes there. So I'll do an example somewhat like these under the discussion area on Blackboard, just to clear up any misconceptions. They don't have to be equally likely categories. That's just the simplest example to do. Anyway, there's the goodness of fit test. Section 22 is going to build on this. In other words, we will do a specific, slightly more arcane type of goodness of fit test. The superstructure of the problems will be exactly the same, but the computation of the chi-square statistic is going to be a little bit more complicated. It's kind of important to understand that what we do in Section 22, because it is comparatively complicated, is literally just building on top of this. In other words, they are complicated examples of exactly this type of thing. But before we can do that, we'll talk about Section 21, which is a little simpler. It's much more like the early part of the course, comparing to categorical variables. These 3 sections are kind of roundabout, but they all go together. The goodness of fit test in general, comparing categorical variables, which is very data analysis, early part of the course type stuff, and then those previous 2 sections, 20 and 21, come together in 22, where we can talk about testing categories to see whether they are plausibly independent of one another. That's ultimately where we're going with these 3 sections. You can test theories, for instance, as to whether men and women have different chances of being left-handed, or whether people in each of 50 states have the same likelihood of being left-handed, and so forth and so on and so on. In order to do this, we've got to start out a little less ambitiously in Section 21 by talking about two-way tables, which is comparatively boring. It's relatively easy to do. It's just computing some percentages, but it doesn't mean that it's not interesting. We can talk about some stuff like why you're more likely to die at sea if you're wearing your life jacket, and all of the clever ways that you can abuse statistics to come up with nonsensical conclusions. So that'll make it a little bit interesting to make it a little less dry than it would otherwise be, and that'll be Section 21.